Lecture 5 of Advanced Inference in Graphical Models. Today we're going to be doing a number of other things that are still, believe it or not, in this treeinference.pdf chapter. That's a big chapter, but I think that if one has mastered the material that is in, that we've been talking about the past couple of lectures, then we'll be very, very ready to master the material that naturally comes next. So that goes without saying. So today what we're going to be talking about is triangulated graphs, the notion of triangulation, and generalizing this idea of how when we saw in the pure tree inference case that we could reuse messages and reuse essentially the process of taking a tree and turning it into an inference strategy for any of the clique marginals that we might want, we'll be able to do the same thing essentially for triangulated graphs. And there's going to be some good news and some bad news. The good news is that there's going to be a lot of potential reuse, and that once we're in the family of triangulated graphs, there's going to be all sorts of great things that happen, very similar to what we saw happen in the case of trees. The bad news is going to be it's going to be very hard. Well, I should say another bit of good news is that it's going to be very easy to find a triangulated graph. The bad news is that it's going to be very hard to find an optimally triangulated graph. So while we can deal with triangulated graphs, it's not an easy prospect to find the best one. And so we're going to formalize that idea in today's lecture. So another way of looking at today's lecture is a little bit of poetry, which I'm notoriously bad at, but I will try to attempt to read it nonetheless. To tree or not to tree, that is the question. Whether it is nobler in the mind to suffer the slings and arrows of non-triangulated models, or to take arms against a sea of cycles, and by opposing, chord them. So if you're interested in the poetic aspect of today's lecture, this is essentially what we're going to be talking about. So a little bit of review. So first of all, these are just a review of a couple of important lemmas and that we just need to essentially gain an intuitive sense for. The first one says that when we run elimination a second time on the reconstituted graph using the same order that we ran in the original graph, then the set of neighbors of any node V that we eliminate at the time that we eliminated in the original graph is exactly the same as the set of neighbors that we encounter when we run elimination on the reconstituted graph. And so that lemma allows us to do things like, for example, saying things like, if we've got an elimination order, then the computational complexity of the elimination process is order r to the k plus 1, where k is the size of the largest set of neighbors encountered during elimination, even in the original graph, and which by the previous theorem is also the size of the set of neighbors that we encounter, the maximum size of the set of neighbors that we encounter in the reconstituted graph. We define the notion of a perfect elimination graph. A perfect elimination graph is one for which there exists a perfect elimination order, and a perfect elimination order is one such that every node that we encounter has its neighbors in the current graph being complete, meaning that you can eliminate it without causing any additional fill-in edges, or any fill-in edges at all. And when we run the elimination algorithm, this is another important theorem. When we run the elimination algorithm, all the max cliques in the resulting reconstituted graph, all of the maximal cliques in the resulting reconstituted graph are encountered as elimination cliques during the elimination process in the original graph. So that basically means that you've got all those cliques, that you can find all of the cliques in the reconstituted graph just by running elimination in the original graph. And in fact, this theorem is even a little bit, can be strengthened a little bit by saying, in some sense, that when we run the elimination algorithm on the original graph, it's easy to find the set of max cliques in the reconstituted graph. And the way we do that is by noting that any clique we encounter is never going to be a subclique of any future clique because the fact that we've eliminated that node. So it must be a subclique. It must itself be either a max clique or a subclique of a previous clique, and then we just maintain this list of max cliques. And if you're not a subset of some previous max clique, you're a clique, which proves the theorem. And that basically means that the first clique you encounter, the first node you eliminate, no matter what node you eliminate, is going to be a maximal clique. That was a lemma that we saw last time. We also defined the notion of an embedding. And we can say we can embed one graph into another graph if the other graph has the same node set but a superset of the set of edges. So, a spanning tree can always embed in the original graph that it spans, for example. And a spanning subgraph can always be embedded inside of the original graph. And we also defined a triangulated graph as a graph which has all of its cycles being chorded. And remember, what does it mean for a cycle to be chorded? Is that we take any cycle and we sort of highlight that cycle, and then a chord is essentially an edge between two non-adjacent nodes on that cycle. Okay? And all cycles must be chorded. 3 cycles are sort of trivial. We don't even need to worry about them, and in fact sometimes you just don't even consider the case of 3 cycles, but it gets really interesting and meaningful in the case when you have 4 cycles of length 4 or more, when there's a possibility of having a non-chorded cycle. Okay, the other theorem we have, if we have a graph at an elimination order, and then we get this perfect elimination graph G prime, the reconstituted graph by running elimination on G, then we can reconstruct a perfect elimination order with respect to G prime, the reconstituted graph, by repeatedly choosing any simplicial node. So remember, a simplicial node is a node whose neighbors are fully connected in the current graph. So if we keep choosing simplicial nodes and we eliminate them, we're not going to create any cycles, obviously. And we said that the order might not be the same, but we did say that both are perfect elimination orders. Now, what we didn't say is, is it possible for there to be more than one perfect elimination order in a perfect elimination graph? And we're going to visit that in the next theorem of the non-review part of today's lecture. And then the last important theorem that we proved last time was by saying that the notion of triangulation, a graph is triangulated, that notion is identical to the notion that all minimal separators are complete. So remember, a minimal separator is a minimal AB separator for some A and B, and a minimal AB separator is one such that any subset of the separator is no longer an AB separator. Okay. And we also saw examples where a minimal separator can be a subset of another minimal separator. But the main point is that you take any minimal separator for any AB, it has to be complete. And if that's the case, then your graph is triangulated. Question?
Yeah, so complete means everything is clicking to each other?
Everything is connected to each other. Every pairs have an edge. So complete is a graph theoretic notion for all vertices are connected to each other. That's the dual notion to another graph theoretic term that you probably should be familiar, and I might rattle off at some random time, which is the notion of independent. So a set of nodes are independent if none of them are connected to each other. So sort of the dual or the complement of a clique is an independent set in a graph. Okay, any questions on the review? I will take this opportunity to drink water while everyone ponders what possible question one might possess. Okay, that's the water test. That means there are no questions, means everybody understands everything. So let's charge forward. Okay, so this is a theorem that basically means that it's meaningful for the earlier theorem that talked about identifying another perfect elimination order in a perfect elimination graph. It means that exists. And basically what it says is the following. It says that if you have a triangulated graph, then the graph is either a clique, because all cliques are triangulated, which is another name for a complete set. So it's either a clique or the triangulated graph has two simplicial vertices, at least two simplicial vertices. And so this should very much remind you of the property that we saw in the case of trees when we said that a tree has at least two leaf nodes. And in a tree we saw was a triangulated graph. And what are the simplicial nodes of a tree? They are the leaf nodes, right? And so that means that in some sense we're starting to get the idea that maybe a triangulated graph is kind of like a generalization of a tree. And we're in fact going to see that over and over again and very strongly. And that's essentially going to be our connection from inference on any graphical model that's not necessarily a tree back to the inference on trees, which we already know how to do. And essentially it's going to be the same thing, which is maybe interesting and amazing and surprising. Okay, so how do we prove this? Let's just go ahead and prove it very simply. So basically saying that any triangulated graph has at least two simplicial nodes. So if you're a clique, you're triangulated, right? And all nodes are simplicial. So let's assume that the graph is not a clique, and then do an inductive proof. Most of today's proofs are going to be induction in one form or another, typically on the number of nodes in the graph. And so we just sort of verify via enumeration that if we construct any graph that has up to 3 nodes, whenever it's triangulated, there are going to be at least two simplicial nodes. And we can just do that by elimination, very simply. Okay. So next, we assume that it's true for n minus nodes and show that it's true for n nodes. So we're going to use the notion that every minimal AB separator is complete. So we're going to say AB, let's say AB are two non-adjacent vertices. Okay, because it's not a clique, so that means that such a pair of vertices exists. And let's say that S is a minimal AB separator, which by the previous theorem must be complete. Okay, and then let GA and GB be the connected components of the induced graph on V except for S. So this is again this notion that maybe I should add a picture about, again, if this isn't clear. So we've got this separator here. Here's a separator, and maybe here's A over here, and here's B over here. And we're going to come back to this picture a lot in today's lecture. And there's this stuff over here that involves A, and the stuff over here that involves B. And there's other stuff here. And this is G of A, and this is G of B. And then G of V except for S is basically this and that together. It's all of the stuff. It's the induced graph except for S. So it's basically a graph that has all of the edges over all nodes in G except for S. Okay, so just keep that picture in mind. So that's GA and GB. And let's say that A is the vertex set of GA, and then B is the vertex set of GB. And so from the induction hypothesis, by induction, we have that these subgraphs are either cliques or can claim two or obtain or have two simplicial nodes because of induction, right? So basically, the idea is the following. Let me just go to the picture to explain it. So basically, it says that either it's the case that, say, this whole bit over here is a clique, and this whole bit over here is a clique, which is possible, right? Because that separator could separate it down, and the two base cases could be cliques. But if those things are cliques, and if S is a minimal separator, then any node, any of the red nodes are simplicial, or any of the red nodes not in S are simplicial, right? Because let's say this node over here, that's part of a big clique that's connected to all of the stuff in GA and S, and so that's a simplicial node. But it's also the case that any node over here is also simplicial, and it's also the case that any node over here and any node over here are not adjacent. Okay, so that base case spans out. It basically means that any of these nodes over in GA and any of these nodes in GB are simplicial. So we do have two simplicial nodes in this triangulated graph. The other possibility that can happen, see if I can erase this stuff. The other possibility that can happen is that this stuff on the left, say, let's use red again. This stuff on the left is not a clique, but there's the base case hold, which means that there exists at least two simplicial nodes. And so the theorem basically says that the two simplicial nodes can't both exist there, because if there are two non-adjacent simplicial nodes, they can't both exist in S, which is necessarily a clique. So one of the simplicial nodes has to live outside of S, over here. And similarly, over on the right-hand side, the same situation happens. We can, whether it's either in the clique or it's the non-clique case, we have to have at least one non-simplicial node living over there. So we have one simplicial node over here, one simplicial node over here. These guys can't be connected directly because S is a separator. So therefore, again, we've decomposed it into a graph that has two non-adjacent simplicial nodes. And that's basically what all this stuff down here says. So we just did this. So the theorem is proved. Any questions? Okay. So let's just do a little bit of a recap. So this is a recap of both last lecture and just a little bit of stuff that we did today. So there's a lot of information here, so we're going to do a couple of recaps in today's lecture. The first thing to remember is that, well, first of all, we did tree graphs, right? And so tree graphs, we saw that we could run elimination, and the elimination was the same as message passing. That's fine. So now we've got these non-tree graphs, okay? And then whenever we do elimination on a non-tree graph, from the computational point of view, we're effectively doing elimination on a perfect elimination graph. Because every time we run elimination, what ends up happening to that graph is that it turns into a perfect elimination graph. And since elimination run on that reconstituted graph yields the same set of neighbors, we might as well computationally have started from a perfect elimination graph to begin with. So it seems like for doing exact inference with the elimination process, dealing with perfect elimination graphs is inevitable. So then after elimination, we've got a perfect, namely a fill-in free elimination graph. We encounter all of the max cliques when we run in elimination, and they're fairly easy to acquire. The elimination cliques are a superset of the set of max cliques. The set of max cliques are the elimination cliques are the set of cliques that we encounter during elimination. The max cliques are a subset of the set of elimination cliques. We can embed any graph into a graph that has more edges. Like, for example, the graph that results by fill-in. If we've got a perfect elimination graph, it's easy to find a perfect elimination order. We just keep eliminating simplicial nodes. Triangulated graphs are chordal, and all cycles are chordal. The definition of triangulated graphs. We saw the various definitions of separators. There's a separator, there's a minimal separator, there's an AB separator, and a minimal AB separator. And we saw the theorem that said that the graph is triangulated if and only if all minimal separators are complete. And then we saw that any triangulated graph on at least two nodes has two simplicial vertices. Okay, any questions on any of these things that we saw? Okay. So, question for you. In a triangulated graph, are all nodes simplicial? Sanity check. No. The theorem we just proved, right? It's not the case that all nodes are necessarily simplicial. That picture that I just saw, any of the dots on the left and the dots on the right, which are separated by this minimal separator, in that graph. So remember this graph here? So this graph here and this graph here, and S was there. Right? So which are the, and this is GA, and this is GB. It's the triangulated graph. Which nodes are not simplicial? The nodes in S. That's right, the nodes in S. All of the nodes in S. Because these nodes are connected everywhere over here and everywhere over there. They have neighbors which are not connected by an edge. That green edge doesn't exist. if G is triangulated and V is simplicial, and we eliminate V, is the induced graph on V except for V still triangulated? No? Why not?
It could be the only one that takes up the...
So V is simplicial.
If it's simplicial, never mind, yeah.
Yeah, if it's simplicial, that means that any cycle going through V necessarily must have a chord because all of its neighbors, you have to get to V from its neighbors, right? And so all of its neighbors must have an edge. And so if you get rid of V and its incident edges, you haven't created any new cycles, you've only removed cycles. And so the residual graph without V and its incident edges can't have a cycle, a chordless cycle. So, to sort of summarize this, basically we have this corollary that says that in a triangulated graph, there exists an elimination order. There exists a perfect elimination order. And so if we know the graph is triangulated, we can easily find a perfect elimination order. Why is that? How do we do that? Yeah, we just keep finding simplicial nodes. We know there always exists. We find a simplicial node eliminated. We're guaranteed that after we eliminate a simplicial node, it will still be triangulated. If we eliminate a non-simplicial node, is the graph guaranteed to still be triangulated? No, but we know in a triangulated graph, there are always going to be simplicial nodes. So we can easily find a perfect elimination order. In fact, we can strengthen this theorem that says that if G is a graph and there exists a elimination order, then G is triangulated. And just to sort of make this complete, we prove this again by induction. It's obviously true when you have one or two nodes. And we assume it's true for n nodes, and we're given an n plus 1 graph. And so we're assuming that there exists a perfect elimination order, right? And so since there exists a perfect elimination order, there exists an elimination order without fill-in. And so there exists a simplicial node where a chordless cycle cannot exist to that node, since all of its neighbors are completed. We've already sort of done this, right? So once we eliminate that vertex, no fill-in is created, we're left with a graph of size n, in which case the induction hypothesis holds, hence proved. So let's summarize this by the following bijection. If a graph is triangulated, if and only if it's the case that there exists a perfect elimination order over the nodes in G. So that's another way, a very quick way of identifying triangulated graphs. Trees are obviously triangulated. The 4 cycle is obviously not triangulated since there's no node you can eliminate that is simplicial. There's no simplicial nodes in a 4 cycle. But as soon as you chord the 4 cycle, there exists 2 simplicial nodes, as there should be, because it's a triangulated graph, which must have at least 2 simplicial nodes. And then we also have this, which is that if we take any order on any graph, then the reconstituted graph is necessarily triangulated because it has an elimination order now, perfect elimination order. So it's easy to triangulate a graph, right? We just eliminate it, reconstitute it, and we've got a triangulated graph. Is that good? Does that mean that it's a good triangulated graph? Does that mean that it's something that's going to be cheap? Because remember, all of this has to be seen in light of what ultimately we're really trying to do here, which is to compute probabilistic inference queries. And when we eliminate a node and we create fill-in, what we're really doing is we're coupling together factors. And so we're going to get back to that important. But here's an important sort of thing that basically says that we can generate a reconstituted elimination graph using the reverse elimination order. So has anyone seen the animation at the beginning of the YouTube lectures? The beautiful, amazing, incredible animation that obviously came from Disney. It almost got into the movie Frozen, but then it was taken out, that little animation. So no, nobody knows what I'm talking about. So what this says is that if we run the elimination order, we run any elimination order on any graph, we know that the reconstituted graph is triangulated. But we can regenerate that triangulated graph by using the elimination order in reverse. And the way we do this is the following. So I'm just going to draw a picture that sort of explains this algorithm. So we go backwards. We start at n. Then we start with an empty graph. And then we say we start by putting down the last node. So that's the last node to be eliminated. And that's always going to be a graph of size 1. And then the second to last node, the penultimate node, is added. And that's connected to only one graph. So let's call this guy n here. And this is n minus 1. Okay. And basically, then the third to last node is this one. And we connect it to the previous set of neighbors. This is n minus 2. And then maybe another node is then connected to the set of neighbors. The key thing is that what happens is that we're always connecting the previous node, when we add to it, to a set of fully connected nodes. So if this is n minus 5, we connect it to this one, this one, and this one. So is this a triangulated graph? So now, like for example, we have the option to connect n minus 6 to any complete set. So we could connect it to either these two, or we connect it to these three, or we could connect it to these ones. Because the idea is, since it's a reverse perfect elimination order, since it's a perfect elimination order, it has to be the case that if we run the reverse perfect elimination order in reverse, meaning we run it forward again, it has to be the case that every node is simplicial. So if we eliminate, so this is what's great about using the iPad. I can create animation on the fly. If we run the reverse elimination order in reverse, so let's eliminate n minus 6. So is n minus 6 simplicial? Is it? Yes. It's all its neighbors are complete, so we can just eliminate it. Let's eliminate next n minus 5. Is n minus 5 simplicial? Yes. So we do that. And then we eliminate n minus 4, and so on and so forth. So we keep eliminating stuff in reverse, and we are just running the elimination order forward again. Let me just put this figure back, so for posterity reasons. So that's essentially what this algorithm does. Now, you might think, well, why do we care about this algorithm? Because it's going to be an important part of a critical algorithm for identifying when a graph is triangulated, called maximum cardinality search. So this is sort of a precursor to the maximum cardinality search algorithm that we will see later today. Any questions on this? Yeah.
When you connect to n minus 3 node, you connect it to both n and n minus 1. Is it not possible that n minus 1, n minus 3 is only connected to, say, n?
Sure. Absolutely.
So
I mean, this is an arbitrary reverse elimination. I just made this up on the fly. This is not necessarily the graph. There is no the graph. This is just, if you take any graph that's not triangulated, run elimination order forward, then consider running it backwards. If you run it backwards, what's happening is like you add the node, the n minus kth node, and then you connect it to the set of neighbors that it had at the time it was eliminated. Necessarily, it's going to be the case that that you're creating this reconstituted graph, those neighbors are going to be complete. So when I ran this thing backwards, I connected n minus 3 to n and n minus 1. I could have connected it to any complete set. At that point, when n minus 3 was added, there were only two complete sets. It was either n and n minus 1 or n minus 1 and n minus 2, in which case I would have had a different graph, because there's no edge between n minus 3 and n minus 2. But I just chose that arbitrarily, just to give an example. But the point is that, try a graph. Try running elimination forward, and then you can run it backwards. Now, running it backwards, like I said, you might wonder, why is this important? And the reason why it's important is to get the idea of the elimination backwards, because we will see that in a very, very important algorithm, MCS, maximum cardinality search. We will see in a minute.
So if you have taken a different choice of node connections, and in the end, say after like 10 different nodes, we get two different graphs, will the distributions sort of maintained by those graphs be same?
So remember, this is a deterministic process. So we are using the elimination order that we produced, that we ran forward, and we're just running it backwards. So we're not going to get two different graphs. We're going to get the reconstituted graph. This is a way of producing the reconstituted graph that elimination causes. So there is no two different graphs. There'd only be two different graphs if you ran it backwards for two different distinct elimination orders, and that's not even guaranteed to be two different graphs. I mean, you can actually have more than one elimination order that produces the same triangulated graph. But in this case, all we're saying is that we're taking this elimination order. There is some elimination order that we used on the original graph, produced a perfect elimination graph. But the question is, how do we produce that perfect elimination order graph? We can run it this way. We can produce it this way, this backwards way. And this is exactly what that animation at the beginning of the YouTube lecture is showing. In the case when every time we go backwards, we produce a new node, we're connecting it to two neighbors that are complete. Notice that it never connects it to more than two or less than two, and notice that also it never connects it to two disconnected nodes.
Yes. But in that scenario, if you have connected n minus 3 to n minus 2 and n minus 1, and not like n minus 1 and n minus n, and if n minus 3 had some physical notion connected to that particular node, then our relationship between, and say all the nodes have some physical meaning. So the connection between n minus 3 and n minus 2 will provide us with n minus 3 and n minus n. So we just sort of
Sure. It doesn't have the same relationship, but that's not the graph that we produced when we ran elimination forward. Okay, if this isn't clear, then ask me after class or during the break. Okay, because okay, any other questions? So trees can be generated this way. In fact, here's a way of generating a tree. We saw this at the very, very beginning. In fact, remember the definition of the tree, the very bottom bullet point that said we can define a tree by adding a node and adding a new node and connecting it to one existing node already. So any tree can be generated this fashion. So here's a tree, and we're generating it in reverse order. The key constraint is that we can't connect it to more than one node. And so notice that if we then eliminate the tree, we're just eliminating this way. We're just eliminating leaf nodes. That's just the elimination process. So now another question for you, this is another sort of thought question, is does the elimination process span the set of all possible triangulations of a graph? In other words, your graph, okay, let's say you're not triangulated, and there are a large number of possible ways of triangulating that graph. Triangulating basically means adding edges or running the elimination process. Think of there's a finite number of ways of triangulating that graph. One possible way would be to turn that graph into a clique. So the question is, does the elimination process span the set of all possible triangulations, triangulated covers, if you will, of a graph? No. And why not?
4-cycle.
Yes. 4-cycle. Let's do the 4-cycle example. So there's our 4-cycle, right? So how would we, for example, get this triangulation? Right. That we can't get, because as soon as we eliminate one node, let's say we eliminate this node, we add this edge, we get rid of this, there's no way anymore ever to get this edge. That node is gone, so that edge can't be produced. So there's no way of turning a 4-cycle into a clique via the elimination process. Okay, so that might seem... Okay, go ahead. Sorry.
Could you get minimal triangulation?
Yes, that's the next theorem. So that might seem like a limiting characteristic of elimination. But it turns out that elimination has the property that any minimal triangulation, exactly as you just suggested. Now, what is the minimal triangulation? A minimal triangulation is one such that the removal of any edge renders it no longer triangulated. Now, what we mean by minimal, remember, we're starting with an original graph that is not triangulated. We're adding fill-in edges, F, to make it triangulated. And what a minimal triangulation really means is that if we remove any of the fill-in edges, obviously we're not removing any of the original graph edges. The original graph edges are stuck. The fill-in edges, if we remove, a minimal triangulation is one such that if we remove any of the fill-in edges, is no longer triangulated. And what this theorem states is that if you're a minimal triangulation of a graph, then it's possible to obtain it via the elimination process. So let me just read the theorem. So let's say G is a graph, and G prime is the triangulation of it, with F of the required filling edges. If the triangulated graph is minimal in the sense that any subset F prime of the set of filling edges F, and if you take any subset, then G double prime is no longer triangulated, then it's the case then that F, the set of filling edges, can be obtained by some elimination order. And there's a computational consequence of this, which is that you might think this is great, this is all we need to do. But so that's the good news. The bad news is that if you're dealing with non-positive distributions, then minimal triangulations are not state space optimal. If you're doing this is again if you're doing exact inference. And here's an example. It starts with Bayesian network semantics, but let's just do this anyway. So here's a Bayesian network graph here, right here. Okay. It's a Bayesian network, and what we're saying is that D is a child of A and B, and D is the deterministic function of both A and B. So that basically means that if you know A and B, you know D with probability 1. Okay. And then all the other variables, A, B, and C and E, so A, B, C, and E, have R possible values, but D has R squared minus 1 values. Any more values for R wouldn't make sense, because if D is a deterministic if D is a deterministic function of its parents, it doesn't make sense to have more than that many values, because it would mean that it has more values than it could possibly be determined to have. So therefore, let's just say that D has R squared minus 1 values, which is the largest sensible set of values it could have. So then, we didn't talk about moralization yet, but what one has to do when one deals with a Bayesian network is embed it inside of a undirected model, a Markov random field, and that's what the moralization process does. And so the minimal embedding, I'm just going to say, is this thing here. So here's the undirected graph, and this dotted edge up here, this is an edge caused by moralizations. This is a moralization edge. And if you were to say if you eliminate the graph starting with A, it would create this dashed edge, right? And then C, B, D, the cost of that elimination would be R to the fourth. Because what would happen is that once we've eliminated A, so we've created this edge over here, and then next we eliminate C, then we're going to get a clique which consists of B, D, and E, and B and E are both have R possible values, and D has R squared values, and so that means that you have a clique essentially of cost R to the fourth. If we start by eliminating, on the other hand, D here, if we start by eliminating D here, we're also going to have a cost of size a cost of R to the fourth, meaning that the number of terms in the sum is going to be R to the fourth. On the other hand, on the right-hand side is a triangulation of this graph that's not obtainable by elimination, because what it does is it adds both this edge and this edge. We can't get that, because once we eliminate, say, this guy, this edge is impossible to have. And once we eliminate this guy, this edge is impossible to have. So we're adding both of those green edges, which isn't possible through elimination. But that is state space optimal. It has cost R cubed. But it's a non-minimal triangulation, because we can remove one of those green edges on the right and we're still triangulated. So the point I'm trying to say is that the elimination process can give you all minimal triangulations of the graph. But there are real-world cases where if you're doing exact inference, a minimal triangulation of the graph is not state space optimal. Okay, any questions on that? So let's do a little bit of a recap. So to compute the marginals, we must run the elimination. Doing so necessarily produces a triangulated graph. The complexity of the process is exponential in the largest clique of the result. It's nice, we actually learn the complexity when we're doing the elimination. If we're running elimination and suddenly we get this massive clique, we know that we're going to have to deal with that clique when we're summing up the variables in practice. The elimination process necessarily adds edges, namely the fill-in edges to the graph, and then the resulting reconstituted graph is one that the original graph can be embedded into. We can say that the triangulated graph covers the original graph. We can't avoid a triangulated graph. It seems inevitable. And one way or another, when we're doing exact inference in this way, we are implicitly or not dealing with triangulated graphs. And what we'd really like to do is we'd like to find the minimally triangulated covering graph. Namely, we'd like to find the covering triangulated graph that has the smallest, largest clique. Meaning, it has the largest clique that's as small as possible. So that seems to be a purely a graph theoretic problem. So basically it means that figuring out how to do exact inference optimally can be done purely via graph theoretic operations, because we know, at least, let's say that we're dealing with elimination orders. So we're dealing with positive distributions, one for which we know that a minimal graph will be state space optimal. That means that if we just consider all possible elimination orders and take the one that has the smallest, largest clique, then we'll be optimal. The problem, however, is that there are n factorial elimination orders, and we can't try all of them. So the question is there a smart way of finding elimination orders, that we can find the optimal one? So we shall see. So a couple of other definitions. So this is an important definition. So raise your hand if you've heard of a K-tree. So K-tree is a really important graph theoretic construct that anybody who is interested in machine learning and graphical models should be aware about. So basically, a K-tree is a generalization of a tree. First of all, a regular old tree is really just a one tree. So K is equal to 1. And then a K-tree is basically generated as follows. This is one definition of a K-tree. It says basically that any clique of size K plus 1 is a K-tree. And then to generate a K-tree with n plus 1 nodes, starting with a K-tree with n nodes, is we take a new node, the n plus first node, and we connect it to any set of K nodes in the existing graph that's already complete. So how would we generate, let's just do this very quickly. How do we generate a one tree? So let's just start off with a tree. So there's a one tree with 3 nodes. So to generate a one tree with 4 nodes, we take the new node and connect it to any existing set of nodes that are complete of size K is equal to 1. So in this case, we can connect it to any one node. Now we could also connect it to this node, or we could connect it to this node. I mean, we get different K trees, or we get different trees. But the point is, that's essentially a sort of a grammar, essentially a way of generating all of the one trees. To generate a 2 tree, so let's start with a base case. A complete graph with K plus 1 nodes is a K tree. So a complete graph with 3 nodes is a 2 tree. So this is a 2 tree. And then to generate a 2 tree with 4 nodes, we produce a new node, and we connect it to any set of 2 already connected nodes. So that would be 1. To generate a next one, we could just do this, and we just each time we add a new node, we connect it to two nodes that are already connected to it. So we connect it to a 2 clique. And we can just keep going with this, right? As long as you want. Now, how would we generate a 3 tree? So to generate a 3 tree, we'd have to start with any set of 4 nodes that's complete is a 3 tree, right? So we have to start with this thing. And then to generate a 3 tree, we take a new node and connect it to any 3 nodes that are complete. And so on and so forth. So any complete n-graph is an n-1 tree, trivially. A regular tree is a 1 tree. And all k trees are triangulated. Why is that?
If you look at the way we generated the k tree, we always added a node that we connected with k number of edges to their neighbors that are already connected.
That's right. Exactly right. Yeah. A k tree is always triangulated because we can always construct a perfect elimination order in the reverse order that we use to generate the k tree. Because in the reverse order, it's always going to be a perfect elimination order, because when we do it in the reverse order, the last node we connect is always going to be simplicial. Then we eliminate that. Then the penultimate node that we added is also going to be simplicial in that node. And we keep just going backwards in that order. And that's going to be a perfect elimination order of that k tree. So any k tree is triangulated. Here's some examples of 2 trees that are a little bit nicer than the one I just drew. But you can see, you can eliminate these 2 trees. Like, let's do some elimination. We can eliminate that guy, we can eliminate that guy, we can eliminate that guy, and now we can eliminate this one, this one, and this one. And now we can eliminate this one, and now we can eliminate that. And so basically, we've got this perfect elimination order. This one over here on the right, we can start eliminating this way. These are sort of branches. And so on and so forth.
So, just a quick question. When you come to the last 3 nodes, for example, on the left hand side example,
Yep.
you have a complete graph, so it doesn't matter which node.
That's right. That's right. So on the left-hand side, the question was, you've got, so this is the base case. Any complete set of 3 nodes is a 2 tree. And in that case, you can eliminate them in any order you want. It's always simplicial. Because any complete graph, all nodes are simplicial. Okay, so what do 3 trees look like? These are some pictures of 3 trees that are drawn in a similar way. And here, with these pictures, you can kind of get a sense of why they're still trees. And in some sense, they're kind of like thick trees with a width of a tree wider than a 1 tree. A 1 tree is kind of like a skinny, twiggy tree. And a k tree is kind of like a k-thick tree, right? So here's a 3 tree. And you can see that there's sort of a grid-like structure that's thicker than this. One thing also that's kind of interesting is that you can see that like these are the separators. The separators in a k tree are size 3. So there's a separator. Like that sort of splits the tree into 2 sections. In a 2 tree, the separators were of size 2. So that, in fact, is a property of k trees. In a tree, all minimal separators are of size 1. I should have said that these are minimal separators here. These are minimal separators. In a tree, all minimal separators are of size 1. In a k tree, all minimal separators are of size k, and thus a k clique. In a k tree also, all maximal cliques are of size k plus 1. So the maximum size clique is also, of course, size k plus 1. So that means that the complexity in a k tree is going to have complexity order r to the k plus 1, where, again, we're assuming that all random variables have the same number of values. Is that a question? No. So more strongly, we can essentially define a k tree as a graph which has the following properties. It has to be connected. Its maximum clique is of size k plus 1. And every minimal separator has to be a k clique. A k clique is a complete set of size k. So there's also this notion of a partial K-tree. So any spanning subgraph of a K-tree is a partial K-tree. And so what this means is that any partial K-tree is embeddable into a K-tree. So the notion of embedding makes sense here as well, because if you're a partial K-tree, that means you're a subgraph of a K-tree, which necessarily means you can be embedded into a K-tree. And so that means that inference in a partial K-tree is at most r to the k plus 1 as well, right? Because if you can embed a partial K-tree into a K-tree, you can basically do inference at most order r to the k plus 1. So we do know that K-trees are triangulated, but an arbitrary triangulated graph is not necessarily a K-tree. We know that, right? Because it's not necessarily the case, using that previous lemma, that in an arbitrary triangulated graph, the minimal separators are all the same size. In fact, we even saw an example last or 2 lectures ago where minimal separators can be subsets of each other. Obviously, they're not the same size. However, what we do have is that any triangulated graph can be embedded into a K-tree for a large enough K. And you can sort of think about what we're trying to do here. Like, the problem and the tools of K-trees that what we're trying to sort of get at is that we want to sort of take a triangulated graph and embed it into a K-tree for K being as small as possible. Now we can trivially embed it into a K-tree for a large K. Like, for example, we can set K is equal to n minus 1. That basically turns it into a clique, and we can embed any graph into a clique. Now that's not a very helpful or useful embedding, but it certainly means that it's true. Now the question is, however, and it gets much more interesting when you're asking, can you embed an arbitrary triangulated graph into a K-tree for this, or how do you embed a triangulated graph into a K-tree for the smallest possible K? And that's basically this question here. So the theorem basically says the following, that if G's triangulated graph with at least k plus 1 vertices, and it has a maximum clique of size at most k plus 1, then G can be embedded into a K-tree. Okay, so the proof is actually really neat, I think. It's a really interesting proof. So basically, we're starting with a triangulated graph, and so we know that there must exist a perfect elimination order. Right? There's the perfect elimination order for G. So what we're going to do is we're going to embed G into the K-tree by adding edges to G, so that same ordering that was perfect in the original graph is also perfect for the K-tree. Okay, so we do this inductively. So how do we do this? So the first thing we do is we say that in order for it to be a K-tree, we said that any clique of size k plus 1 is a K-tree, right? So what we do is we take the last, we're running this elimination order, and we take the last k plus 1 vertices. This is a set of size k plus 1. And it's the last set of vertices. We just sort of turn them into a clique. Okay? And then the next thing we do, the induction hypothesis, is that basically we're assuming that we've embedded this remaining set of vertices to be eliminated into a K-tree, and now we've got vertex sigma I to embed. Now we know that at the time that we eliminate vertex sigma I, since the max clique is of size k plus 1, we know that this vertex must be adjacent to a clique with no more than k vertices, right? Because basically we said that the max clique in the original graph is of size, in the original triangulated graph is of size k plus 1. So that means that sigma I can't be adjacent to more than k vertices. And let's say that C is that clique, right? Now C is essentially a set of vertices in that future set of vertices that we're about to eliminate, because remember, we're running backwards in time. And so in that K tree, that we got from the induction step, this set of adjacent vertices is contained in a K clique C prime, because it's a K tree, right? And so what we do then is we just make sigma I adjacent to all of the vertices in the clique C prime that contains C, which was the original set of vertices that sigma I was adjacent to in the original graph, in the original triangulated graph, when we eliminated sigma I. And then this is going to produce a K tree, Ti, because now sigma I is still going to be simplicial in that graph. And then that's the induction step. And then we just repeat this process all the way back to sigma 1. So maybe an example would help this a little bit, and let's see if I can think of an example. The question is, okay, so there's a triangulated graph, right? And I should have numbered these first. So let's do this. Let's say that this guy is 1, 2, this is the reverse number, 3, 4, 5, 6, 7, and 8. So this is the number that we use to produce this graph, probably, or something close to it. Okay. So let's say, is this a 3 tree? Can it be embedded into a 3 tree? The largest clique is of size 4. Okay, so can it be embedded into a 2 tree? Can it be embedded into a 2 tree? No. Can it be embedded into a 2 tree? So 3. So how can we then turn this into a 3 tree? Well, let's start with, so I'm going to use different color edges for these additional edges that we're adding. Let's use maybe green or something. So, and this is going to get messy because I didn't plan this out to begin with. So we do 1, 2, 3, and 4. So 1 and 2 and 3 and 4 are not a clique, right?
Are you writing it? Is that true?
I'm sorry?
Were you just writing? Never mind.
Was I just writing?
I thought you were writing on there and it wasn't showing.
No, now I'm writing on there. Now I'm not writing on there. This is writing, not writing. The first thing we have to do in order to be embedded into a 3 tree is what? What does the theorem state? So let's go back to the theorem and just see what it says. So we have to have a base case of k plus 1 vertices. So we have to take these first 4 vertices, or I should say these last 4 vertices, 1, 2, and 3, and 4, and turn them into a clique. So like I said, this is going to get a little bit messy. So I think that's a clique now. So next we take the next vertice, 5. So 1, 2, and 3, and 4 is a 4 clique, which is therefore a 3 tree. So now we have to take the next vertex that we produced, which is number 5, and 5 has to be made adjacent to a set of size 3 that's complete in the previous set. So 5 right now is adjacent to 4 and 2, but it's not adjacent to 3. So we need to add an edge. So let's say that add this edge. Okay, so is 5 now adjacent to 3 vertices in the set of previous vertices and that there are a clique? Yes, because it's adjacent to 4, 2, and 3. Now 6 is kind of already done, right? What about 7? 7, we need to connect it. So what should we connect 7 to? You want to do 5 and 6? Okay. You like long distance edges. I was going to do some short distance edges, but sure, let's do long distance edges. Okay, 5 and 6. Can we do 5 and 6? Is that right? So what about 3 and 6? Can't do that. Because 3 is not connected to 6. So we can connect it to 5, but we can't connect it to 6. We can connect it to 2. Because it has to be connected to a clique, right? So now 7 is adjacent to 2, 3, and 5 in the set of previously constructed neighbors. So we can still have a long distance edge from 7 to 2, but maybe not quite as long distance as to 6. Okay, so the last one is 8. So 8 is connected to 7 and 3. So the natural edge would be, let's use a different color, would be, what color have I not used yet, to 5. Okay. Okay, so now is that a K tree? Is that a 3 tree? Yes. We can eliminate 8 and 7, 6, 5, 4, 3, 2, 1. It's a triangulated graph, and it's the case that every time we eliminate nodes up until we get to that last final 4 clique, it's the case that we have 3 complete adjacent neighbors, hence it's a 3 tree. And what we've done then is embedded the original graph, which was written in black, into this larger K tree, which have these additional edges that are in color. And that's essentially what the theorem states. Okay, so then the reconstituted eliminated graph can be embedded into a K tree for large enough K. Okay. So you might think, why do we care about this? I mean, there was a question the other day where we said, well, we're talking about the complexity of things like order r to the k plus 1, and we're not worrying about the n. And here it might be the case that, like, say, we have some long chain, and then suddenly this giant clique at the end of it, kind of like a lollipop, the lollipop graph, where it looks like this, right? And if we were to embed that graph into a K tree, especially if the chain was really long, like let's say the train was much larger than the number of variables in there, then in some sense there would be some waste here. But again, we're sort of thinking of this asymptotically. We're thinking about asymptotic growth as n gets larger, and we're sort of assuming k, which is the size of the largest clique in the triangulated graph, sort of stays fixed. So we don't really care right now about n here. Okay. So basically, what we're saying is that in our reconstituted perfect elimination graph, we might not only have one clique that is of size k. So when we have a K tree, we actually have potentially lots of cliques that are size k plus 1. But it doesn't really change the fact that we have exponential cost in the size of the largest clique, which is the thing that we're trying to get down. So the task we have is then we want to find the elimination order that results in the smallest k, such that the original graph can be embedded into this K tree. And now this will give us, not necessarily this is what we implement, but this will give us a theoretical tool that we can use to answer questions about how difficult this is from a complexity theoretic perspective. And so here's the question again. This is this goal, which I just stated. And the theorem, the sad theorem we have, is that finding the smallest k such that G can be embedded into a K tree, even given all of these other potential misgivings that you might have about this process and about the long chain and the lollipop graph, even this process, just finding the smallest k such that the graph can be embedded into a K tree, is an NP-complete optimization problem. Meaning, like, for example, the yes-no question version of the problem, like, for example, can this graph be embedded into this K tree? That's an NP-complete question. So what this means is that unless p is equal to np, you can't hope to find the optimal elimination order for a graph. So this is potentially a problem, right? Because it means that, I mean, you've probably heard that doing probabilistic inference is NP hard, right? But this is saying finding the strategy for doing probabilistic inference optimally is also NP hard. So it's like a meta difficult problem, because not only is the problem hard, but finding the best way of doing the problem is hard. So this seems problematic. However, there are some really nice heuristics that we will describe next that actually work really, really well. So, are there any questions?
Can you use approximation algorithms for this?
I will talk about that. So there's some hardness results that we have. So we can use approximation algorithms, but the hardness results are not so encouraging. Put it that way. And there's tight bounds even. So let's talk about the heuristics first, then we'll talk about the hardness. So before we do that, let's take a break. Okay, so we're back. One question came up during break is, what do I mean by a positive distribution? It's actually fairly. You will find this definition fairly simple. So a positive distribution. So x is a random vector, right? So x is a vector over n random variables, and a positive distribution is such that for all of x, p of x is greater than 0, strictly greater than 0. So, like for example, a Gaussian is a positive distribution. And a Gaussian, actually, Gaussians themselves are very complex distributions, and we could spend a long time just talking about Gaussians. But it turns out that a Gaussian, when you look at the inverse covariance matrix of a Gaussian, the zeros in the inverse covariance matrix correspond precisely to missing edges in a Markov random field, and the non-zeros correspond to edges. Exactly. So anything you're talking about here with a graphical model, and you want to use a continuous distribution that's a Gaussian, then the zero and non-zero pattern of the inverse covariance matrix of the Gaussian gives you exactly that. But a Gaussian is a positive distribution. And in fact, a lot of this topic came up a few weeks ago. I mean, a lot of this graph theoretic machinery that we're talking about, like for example, Rose's entanglement theorem, and the early interest in triangulated graphs by graph theorists, such as Berg, for example, and other famous graph theorists in the 1960s and 70s, the reason why they were interested in this is because of matrix algebra, sparse matrix algebra. So a lot of this stuff actually corresponds to things that are very relevant for doing efficient matrix algebra for like sparse Gaussians. But it just turns out that that machinery happened also to correspond to describing the complexities of doing inference in graphical models. So we're back here now at this notion of heuristics for graph triangulation. And there are a number of different heuristics that people use, and these are very widely used heuristics for a variety of reasons. So the first one is called the minimum fill heuristic, and so like these are all in some sense greedy heuristics, right? So they're greedy algorithms that basically do something. So what is a greedy algorithm? A greedy algorithm is basically one that does next whatever looks best at the current time. And so the question is, the thing that distinguishes different greedy algorithms from each other is what does it do, and how do you judge what it does as best or not best. And so what it does in all of these cases is basically eliminate a node. And then the difference between these heuristics is how does it judge what looks best. And so in the min-fill heuristic, what looks best is the node that results in the least fill-in. So like if there's a simplicial node, you would always eliminate simplicial nodes. And you keep eliminating simplicial nodes until you run out of simplicial nodes. And then you would eliminate the one that results in the fewest number of additional fill-in edges at that step, where you break ties arbitrarily. The next one is not the one that eliminates that chooses the next node that has the least fill-in, but yields the smallest elimination clique, which isn't necessarily the same. You could actually have a very large elimination clique with a very small fill-in, or a very small elimination clique with a relatively large fill-in. And so you might get different decisions depending on which heuristic you use. So this one basically cares about the size of the elimination clique at the time. A third one is the minimum weight heuristic. So in general, when the random variables don't have the same value, so the first two heuristics sort of work when all the random variables have the same number of values, like R is the letter that we've been using. But it's not necessarily the case that say, the neighbors of a node that you're about to eliminate have the same set of values. And so what you might do is eliminate the node that has the smallest state space, or the smallest weight, where the weight is defined as the product of the states, the product of the cardinalities of the neighbor random variables at the time of that you eliminate one. So those are already sort of some basic heuristics. The question the next set of questions you do is, well, how do you break ties? So in each of those heuristics individually, you'd break ties arbitrarily. Another strategy is like if one heuristic has a tie, you'd sort of back off to another heuristic to help break the tie. And that can actually help sometimes. And then where you really start getting some help is by using non-greedy strategies. So rather than just greedily choosing the best at each time, what we would do is say you take the m best vertices. So that means, for example, like if fill-in is your heuristic, you would choose the top m, namely the m nodes that would result in the least fill-in. You'd sort based on fill-in, because you'd sort ascending based on fill-in, and the top ones would be the ones that yield the least fill-in. And then you choose arbitrarily from the top n rather than the top one. And then another strategy would be to do this randomly, where you'd actually define a probability distribution over the top m. And then you choose either uniformly over the top m, or you choose non-uniformly. You could actually turn the number of fill-in and choose proportionally based on inversely to the number of fill-in, or the size, or any of these other heuristics. You could turn them into random heuristics. And then lastly, where this really, really works, what really makes the biggest difference is that if you do these above random heuristics, you try lots of different ones, and you just try lots of elimination orders, and then you keep track of which one does the best. And the randomness helps you. These non-greedy, random next step heuristics, running them multiple times, in practice can often, strangely enough, yield the optimal elimination order. And the way we know that it can lead to the optimal elimination order is that we run, we've done this ourselves in our lab, we run the optimal exponential cost algorithm to get the optimal triangulation, and then we see that the elimination heuristics, these random ones, got it. And it's often, but on the other hand, like I said, you never, since it's an NP-complete optimization problem, you never know. You could run these things for 1,000,000 years and you might not know. It might not actually get you the optimal. And the difference between the optimal and the suboptimal might be enormous. If your random variables are of cardinality 100, there could be a factor 100 difference in time and memory between the optimal and any suboptimal one. So these things make an enormous difference. So it's usually worth one's time, if one is doing exact inference, to spend some time figuring out a good elimination order of your graph, because if you find that optimal one, you're doing much, much better, oftentimes. Okay. So this is a repeat of the previous slide with a little bit of extra stuff at the bottom, saying, okay, so we've got these heuristics, which we just talked about. Are there any questions on the heuristics, by the way? They really work, actually. They really work well. But on the other hand, you might think of a more non-heuristic strategy for doing this. And when you're interested in non-heuristic strategies, you're interested in the approximability or inapproximability thereof of these strategies. And so there are some very related problems that, in some sense, indicate the difficulty of the situation that we're in. And so this is a very famous NP-complete problem called maximum clique. This was one that goes way back to the early days. And the problem is the following. It's like you're given an arbitrary graph, and what you're trying to do is find the largest clique, largest in terms of number of nodes in that graph. And what this is saying is that that's an NP-complete optimization problem. Now, right away, you might be wondering, well, wait a second. You just said that if you have a triangulated graph, I can run a perfect elimination order on that graph, and I can easily find a perfect elimination order, and the largest clique encountered along that perfect elimination order is the maximum clique of that graph, right? So what does this say? This says that if the graph is triangulated, I can, in polynomial time, find the maximum clique. So if you're given the class a graph that comes from the class of triangulated graphs, I can easily find the maximum clique. But what this theorem 5.4.1 says, however, is that if you don't know if the graph is triangulated or if it's an arbitrary graph, that suddenly, the difference between being triangulated or not, that suddenly makes it an NP-complete problem. So the question is, how hard is this to approximate, this problem, this maximum clique problem? So first of all, what does it mean to approximate? We mean multiplicatively approximate. So what that basically means is that we've got some function f, which is a function of n. That doesn't mean it's not a constant. It still could be a constant. But let's just say it's some function of n. And we say that we have an fn approximation algorithm for this problem if the solution that the algorithm provides is always at least the optimal divided by f of n. So if you like a picture, so like let's say like maybe opt is right here. So we're trying to maximize. We're trying to find the size of the maximum clique, and here's opt divided by f of n. And what an optimization algorithm says is that your solution is no worse than opt divided by f of n. So you're never in the red region. You have to be in the green region. And then what a lower bound would mean is that you can never do better than, say, there's some point at which you can never do better than. So if you could prove that that's the best you can do, you can never say, like, oh, let's say that this is the lower bound here. You can never say that I'm going to be this much better. Then that's the lower bound. That's the idea. So the results that we have, and this is something that we're not going to prove, but just to give you the result in the reference, is that there is an algorithm that does order n over log n squared. So that basically means that opt divided by n over log n squared, you can do, it says that you can do no worse than that. Okay, and that was a result that came out a number of years ago in the 90s. But the bad news is that it's inapproximable to do better than order n to the 1 minus epsilon for any epsilon greater than 0. So basically what it means is that the Bopana and Halsdorson result is tight. So that's the best you can possibly do. So basically it means that it's order n inapproximable, to put it very, very simply. So it means that as the number of nodes grows, you're going to do worse and worse and worse. Right? It's not a constant factor approximation algorithm. Now, you might think that our problem is this notion of embeddability into a K-tree, right? And so the question is, if it was the case that we could find the smallest k such that it could be embedded into a K-tree, how could we identify in polynomial time in n the largest clique in the original graph? So this I'm going to leave as an exercise for you, so you can think about all this stuff. Okay. But then this will get back to your question about the hardness. And so this is really the connection. So doing this thing that I highlighted in red doesn't involve that much digging into these references, I can assure you that. Okay, so here's another view of the difficulty. Like, for example, just viewing it as a problem of fill-in. So finding the smallest set of edges that triangulates the graph is also an NP-complete problem. And this is not saying finding the smallest k. This is basically saying I'm just measuring the problem, measuring the goodness of the problem in terms of number of additional edges, the size of f. That's also hard. So we're sort of really dealing with a range of problems, namely finding how best to do inference, exact inference in graphical models. We're dealing with a problem that's very, very hard. And thus P is equal to NP. Okay. So that's the bad news, generally. On the other hand, there is some good news. And so let's talk a little bit about the good news. Any questions about the bad news? Okay. Any question about the good news? So the good news is, well, we've already seen this, that if it is the case that there is a perfect elimination order, the graph is triangulated, right? And what we could do is we could then use that fact to test for chordality. Like, for example, this problem of finding the maximum clique in a graph. We said that if the graph is triangulated, we can actually find that. So maybe we could just keep trying to identify simplicial nodes, and if we find simplicial nodes and eliminate them all throughout the entire graph, then we are assured that we have found the maximum clique in the graph, and also that the graph is triangulated. And if it's the case that we ever encounter a non-simplicial node, then we know that the graph is not triangulated. Okay. The problem with that algorithm is that when you implement this naively, it's going to be an n-cubed algorithm. Because, for example, like there's n nodes you have to eliminate, and each time you touch a node, it's going to be potentially an n-squared problem to see if all the neighbors are connected. So it turns out that there's the maximum cardinality search algorithm. This is a really amazing algorithm developed by Tarjan that can actually do the chordality testing in linear time, or linear in the number of nodes and number of edges. So how does this work? Is that what the algorithm does is it produces an elimination order of the graph, but it does so in reverse. It's very similar to that algorithm we saw a little bit earlier, in the sense that it's producing an ordering of the nodes, but in a reverse order, which ends up being a non-fill-in order if it is the case that the graph is triangulated. And as soon as it detects a violation, it spits out not triangulated. And the way that it does this is by looking, you start labeling these nodes, and then you sort of look at, you choose another node based on how much overlap it has based on some set of nodes that have previously been labeled. And each time you choose a node, you look at its intersection of its neighbors with its previous set of labeled nodes. And if it's the case that its previous set of labeled nodes is not complete, then you can now put non-triangulated. So let's see the actual algorithm. This is an important algorithm, so we're going to go through it a little bit. So the input is an undirected graph, and the result is an output which says it's either triangulated or not. And in the case that it is triangulated, we're going to have an MCS ordering of the triangulated graph, which is going to be perfect for that triangulated graph. So we start out by saying L is a set. L is going to be the set of labeled nodes. Okay, so it starts out being empty, and we just have a counter. Okay, so we repeat this loop from here to here, while it's the case that there are unlabeled nodes still remaining. Okay, and then this next step is how the algorithm gets its name. We choose the next node whose neighbors whose labeled neighbors have maximum cardinality. So we choose the node U whose neighbors, delta U, intersect with a labeled set is maximum. So this is the maximum cardinality search. Okay. And then, so we've got this node, and then we then look at C becomes essentially the set of previously labeled neighbors. Okay. And then if it's the case that that node and its set of previously labeled neighbors forms a clique, then everything's great. We add that node to the new set of labeled nodes and continue on. But if it's ever the case that the node and its set of previously labeled neighbors is not complete, then we output not triangulated and exit or something. So it's in some sense very simple, but let's see an example. Let's run it. Which one of these graphs do you want to run it on? Don't choose too simple a one. Let's not use this one. Don't choose too simple or too complicated. But which one would you like to choose? Or any one you want. I don't care. Left bottom first. Okay, let's do this one. So we're going to run maximum cardinality search. So when we first label a node, let's say that the red nodes are going to be the ones that are labeled. Okay. So it doesn't matter. We choose an arbitrary node. So we choose that node. And that guy gets labeled. Okay. So there's nothing next to do except to choose another node. So we need to choose a node that has a maximum, whose set of previously labeled neighbors is maximum. And so we could either choose this one or this one. Which one should we choose? Break the ties arbitrarily. Which one should we choose next? Let's choose the top guy. So this is one. This one's two. We choose this guy. So is that guy's previous set of labeled neighbors complete? So number two, who are two's previously labeled neighbors? That's only one. So this is the previously labeled neighbors. It's complete. It's the set of size 1. So we're good. So the next thing we do is we choose another node that maximizes the set of previously labeled neighbors. How many choices are there? There's one. So this has to be number 3. Choose this guy. Is number 3's previous set of previous neighbors complete? Yes. 1, 2, 3 is a clique. So that's good. We have one last node to choose, which is number 4. Right? Now, is his previously labeled neighbors complete? Who are 4's previous labeled neighbors? 1 and 3. That's a complete set, right? So therefore, the graph is triangulated. So it's always the case that when we choose a node, its set of previously labeled neighbors are complete. So that's a triangulated graph. And let's do this one. I'll just do this one really quickly. So we choose. Let's say we choose this one first. Okay, so that one's chosen. So then we choose another one. We could either choose this one or this one. Let's choose the bottom one. Its previously labeled neighbors are complete. Now we choose this one because it has its previously labeled set of neighbors is 2. This guy's previously set of neighbors are complete. Then we choose this one. These guys are complete. Then we choose maybe this one, and these guys are complete. And then this one, and these guys are complete, and so on and so forth. And so, like, which one would we choose here? We could choose, say, this one, and he's complete, and this one, and all 3 of these guys are complete. This one, and these guys are complete. This one, and these guys are complete. And finally, this one, and these guys are complete. MCS, triangulated graph.
So what about one that's not?
What about one that's not triangulated? How about this page? So which one do you want to do? We've seen these before. Pick one that you'd like to run in real time.
That's the pentagon.
This one up here? This one?
Oh, it's to say this the bottom near the left, the one with the pentagram.
This one here?
Yeah.
Okay. Okay, let's start by picking a node. To make this quick, let's pick this one first, okay? This one first. That's fine. We choose another node, and its previously labeled set of neighbors are complete, right? We choose another node that maximizes. So we can either choose this one or this one. Let's choose G, okay? So its previously labeled set of neighbors are complete, which is F. But then when we choose this one, which is we have to choose that one since that's the node that has a set of neighbors who are labeled of maximum cardinality, we see that these guys are not complete. So therefore, the graph is not triangulated. If we had started down here, we would have messed around with this triangulated portion of the graph. But this way, we got to it a little bit faster. So I did that deliberately. But you can see that in this graph here, let's just do this one. So we choose this node here. Okay, and we can choose any of these 3 next, right? So which one do you want to choose? Bottom. So this one. Is its previously labeled set of neighbors complete? Yes. So which one must we choose next? The middle. Is its previously labeled set of neighbors complete? So which one must we choose next? We can choose either of them, right? So which one should we choose? This one? Everything's fine up until we get to this last guy here. And that's when we detect an error because that edge is missing. Okay, so that's maximum cardinality search. So the theorems that we have are that a graph is triangulated if and only if the maximum cardinality search algorithm at each point when a vertex is marked, that vertex's previously marked neighbors forms a complete subgraph of G. And the other corollary is that every maximum cardinality search of a triangulated graph corresponds to a reverse perfect elimination order of the graph. I will see you on Wednesday.